Hello everyone. On behalf of myself, Shoga Shehi, and my colleagues Asha Naqbi and Shaima Mohammed, we are going to present our research, a hybrid photovoltaic solar chimney desalination plant, under the supervising of Dr. Muhammad Tawalba from the University of Sharjah. Recently, the growth of the global population and living conditions have raised the worldwide demands for water and energy. The energy crisis and the lack of fresh water are two inseparable threats to human life, particularly in remote areas far away from utility grid. Do you know that around 785 million people around the world does not have the access for clean fresh water? And as a result of that, every 2 minutes a child is found dead in different countries. Over the last century, the production processes of both power and fresh water have dominantly been driven using fossil fuels. The use of fossil fuels has shown challenging issues, which are mainly the damage they cause to the environment and the depletion of their sources. Furthermore, attaining the worldwide intensive growing demand for those two crucial resources has necessitated the switching to sustainable energy sources for the purposes of producing them. Among various sustainable and environmentally safe energy resources, solar energy has been found as the most dependable and affordable renewable energy resource. Most importantly, it does not pollute the environment, even during production process, as does photovoltaic production. Solar chimney power plants represent one of the means that have been developed and implemented to convert solar energy into electric power. A typical solar chimney power plant mainly consists of three components: a solar collector, a chimney, and a wind turbine. In this system, solar radiation is collected by the solar collector and it heats up the ambient air entering it. Then, the hot air flows into the chimney through the collector exit, which also the entrance of the chimney. In the chimney, the air density difference between the inside and outside of the chimney causes a large pressure difference between the system and the ambient air, which will drive the wind turbine installed at the chimney base to generate electricity. More details about the proposed system will be discussed by my colleagues, starting with Shaima.
As my friend explained previously, the traditional system produced electricity with low conversion efficiency. Our idea introduced a novel configuration of conventional solar chimney power plant integrated with transparent PV and seawater desalination process in order to produce more electricity and fresh water. Also, this new addition enhanced the performance of the overall system. This system mainly consists of three parts: collector, water pool, and chimney section. In our model, the collector roof is covered by transparent PV cells to generate more electricity, and the water pool is placed underneath of the collector to produce fresh water. In the first section, solar radiation heats up the ground under the collector, then the air is heated up by convection from this ground. This process forms this difference between the air inside and outside the collector, which causes the air to move from ambient to the chimney, passing over layers of seawater in the second section, carrying with it water vapor. While the air is moving inside the chimney, it passes through the turbine installed in the base to generate more electricity. After that, when the wet air reaches to the top of the chimney, its temperature starts to decrease. At this point, water vapor starts to condense, producing fresh water. With this innovative modification, it's not only possible to allow the production of fresh water, but also the water pool is expected to reduce the temperature of the PV panels, thus increasing the efficiency of these panels. Therefore, this would lead to increase the overall efficiency of the system. More details of the purpose of the idea will be discussed by my colleague Aisha.
Low operation and maintenance cost, low environmental impact, and long lifetime. Producing both water and electricity at the same time. High amount of irradiance and temperature levels in UAE. The lack of researches of this field in UAE. Then we did a complete mathematical model for the modified solar chimney power plant. The model consists of several equations that describe the changes of the key variable in each component of the system. The model is designed based on the energy balance equation, which depends mainly on convection, radiation heat transfer, and mass transfer. Then, a case study has been done to estimate the parameters of a conventional solar chimney power plant for a small isolated community contains 30 houses in Sharjah. The optimization of solar chimney parameter for different scales is performed by using MATLAB code after testing different power values. The effect of the required power on the conventional solar chimney power plant parameter, such as collector diameter, chimney height, and diameter will be investigated. The increase of the required power of the system from 400 kilowatt to 1 megawatt led to an increase in the chimney diameter from 9 to 17 meter. Increasing the capacity of the system from 400 kilowatt to 1 megawatt led to a rise in the collector diameter value from 270 meter to 426 meter. The irradiance has a significant impact on the solar collector diameter, with varying the irradiance from 400 to 1000 watt per meter square. The results showed a reduction in the diameter of the collector size by 36.9 for the same output power.
The numerical simulations were performed using ANSYS Fluent to simulate the steady flow and the natural convection problem within the solar chimney system. It involved continuity, momentum, and energy equations which were solved iteratively using the finite volume method based on the Fluent. In this study, a 3D axisymmetric model is developed based on the dimensions as shown in the table. The boundary conditions of the system are clear in the table, since the inlet pressure to the collector and the outlet pressure from the chimney wall are assumed to be gauge pressure equal to 0 Pascal compared to the atmospheric pressure. The boundary condition of the chimney wall is adiabatic, while for the collector roof is assumed as a transparent wall, and the inlet temperature of the air is around 293 Kelvin. The ground is assumed to be an adiabatic wall with the temperature around 295 Kelvin. The simulated inlet air temperature was compared to the experimental result collected from the Spanish model prototype by varying the solar radiation to study the performance of the model. As you can see, the increase of the radiation from 500 to 800 watt per meter square resulted in increasing the temperature of the chimney from 300 to 311 Kelvin. As shown in the table, the comparison of the inlet temperature between the proposed system and the experimental model. As you can see, the error obtained of the model is around 0.3%, which is very low. That indicates that our simulation results are acceptable and reasonable. In this part, we study the variation of the air velocity in the chimney with the solar radiation. The velocity of the air plays a significant role in the amount of the produced power through the turbine. The velocity is around 17.3 for 500 watt per meter square, while it increased to 46.5 meter per second when the irradiance is 800 watt per meter square. The increment of the velocity is around 62.8%, which will increase the power by 95% because the power is a function of cubic velocity. In conclusion, solar chimney power plants are passive environmental systems which produce electricity relying on solar energy. Some of the following recommendations could be proposed for future study, such as building a prototype to study the behavior of the flow in the selected region and to compare it with the experimental results. Furthermore, converting simple system to hybrids with other renewable energy systems to increase the overall efficiency of the system. Thank you.